jump into it?
I am so ready. Okay.
Then we'll look at our smaller amount of audience and say that we're down to the real fans.
We had the
We've gotten rid
real.
of the fake fans of last year
Yes.
or last week.
Yes.
Either
All
way,
right.
take it away with part 2, wonderful slang for quantum
Thank you.
gravity.
Thank you, Bubs. All right. So yeah. Last week we gave it a big start. And went through a lot of stuff. Today I hope we can be a little bit slower and go into a bit of detail about the actual content of GR, and also hopefully check out a bit of stuff that I didn't write down. If there's some time at the end, let's see about that. And I think we'll start with a small recap, maybe, just to get everyone back into the groove. So, recording is running, right? Yes. So, yeah, the overall picture is that we want to quantize GR in the most simple fashion. So by slicing it along different spatial time slices and doing a Legendre transform and getting a Hamiltonian from that. And then basically use the Dirac's old prescription of putting hats on everything, and then you would ideally get a theory of quantum GR. And what I emphasized in all of this is that this is perfectly possible if your manifold is already of a certain type called globally hyperbolic, where you can do this sort of slicing. And also that different slicings certainly are different configurations, and they are related by a symmetry of GR, which is the diffeomorphism symmetry. We're going to learn today that there's a bit of a caveat there, which comes from this restriction to space-like foliations, so ones where the foliating vector field is time-like, and also that we are looking at future-directed foliations. Now, I also went through some FAQ stuff. There was a question by someone outside of the talks about the renormalizability of GR. And I'd just like to comment on that really quickly, because that was I think that's worth expanding upon. It's that in principle, the canonical approach doesn't have anything to say about renormalizability and so forth more than other approaches. But there is work on renormalization stuff in GR, particularly in path integral approaches, which I don't know if I will get into that here at all. But the upshot is there is such a thing as RG flow for GR, even in the non-perturbative sense. And it has some very interesting effects. Particularly, it shows that certain quantities like graviton scattering can definitely be finite to all energies, which is something that you can already calculate in classical GR, however. And furthermore, it also seems to be a generic feature that the effective space-time dimension seems to change as you change the energy scale. That's something that comes out in renormalization studies of GR quite a lot. And just to clarify what I mean by effective space-time dimension, I mean by that a certain thing called the spectral dimension, which measures how much sort of a wave packet that you put at a point spreads apart over time. That's how it's measured. I have lots of references actually. I think for non-perturbative RG results, I would direct you to the work of Frank Sauer-Essig. What's his first name? Wetterich. Astrid Eichhorn. What's his name? The Italian guy. Not Riccati. But there's lots of people in this community that all are working on, well, it's called the asymptotic safety community. But essentially, what they're trying to establish is asymptotic safety for general relativity, so that the RG flow, if you follow it into the UV, actually leads to a well-defined theory that is valid to all energies. That's stuff you can do, but that's unrelated to canonical quantization per se. You could also analyze this in canonical quantization. All right. There was also a question about whether we can please include more examples and more phenomenology. I hope I will get to that near the end of the mini-series, so that I still have some time to look that stuff up. Now, wait, where was I? Right. So last time I reviewed a bit of stuff. In particular, I reviewed the ADM formulation of GR, which is sort of the first stepping stone with which you can then do a Legendre transformation. And I emphasized that there's some connections between geometric objects, such as the extrinsic curvature and the induced spatial metric and all of the canonical variables. Then I showed that there's a new feature of GR, which shows up when you try to do the Legendre transform, which is that some of the momenta, the canonical momenta, are just always equal to 0. And that's a hallmark of gauge invariances. But furthermore, it turns out that the Hamiltonian you get if you just follow the prescription for those kinds of systems, it turns out that the full Hamiltonian is actually just a sum of constraints. So if you impose all of the necessary constraints for the time evolution to make sense, then the Hamiltonian is actually 0. So in order to understand this more properly, I gave you all a summary of a crash course in constraint quantization and constraint systems, and emphasized that there's really two types of constraints: first class and second class. First class is known for generating gauge transformations, and second class instead requires that you switch from ordinary Poisson brackets to this Dirac bracket, which you can then use to actually perform the Dirac prescription of just putting hats and everything. If you keep these things in mind, then you can quantize most systems. Most. At least you can apply the usual prescriptions to most systems. Then I exemplified all of this stuff in the case of a wordline particle in the Polyakov form by showing that it also has diffuse as a symmetry, in this case reparameterizations of time along the wordline. I showed that this is really a symmetry, and I also showed the Hamiltonian analysis, which is very similar to that of GR, and in particular showed that the Hamiltonian in this case is also a pure constraint. So there's a very simple system, the relativistic particle, which also has 0 Hamiltonian. So it's very physically plausible that systems can have 0 Hamiltonian and still make sense. And the connection between this 0 Hamiltonian form and the usual stuff that we know comes from choosing a certain gauge, which allows you to then use the time translation operator, so the 0 component of the momentum, as a Hamiltonian. And what I emphasized with this was that in principle, you have all of this weird stuff with vanishing Hamiltonians and just constraints, and somehow there's no time evolution. But really what this means is you have to provide a notion of time evolution which makes physical sense. And there's just no preferred one coming from the system itself. Now I want to get more specific with all of this and go into the case of the ADM formalism again and look at what the constraints actually look like for GR. So just to recap, we had that this system here is given as a kinetic term and a sum of different constraints. As before, I will denote the constraints by phi I, any of them, and also there are some gauge coefficients ui which possibly will be constrained. Now, we go through the whole quantization prescription again. We start from a kinematical phase space of variables which don't have any constraints on them. So there's the Q and the P. The Q is the spatial metric, the P is the conjugate momentum, which is related to the extrinsic curvature of a slice. Next, we have the other two more auxiliary pairs, which come from the lapse and the shift. The lapse, if you remember, was sort of the time-time component of the metric, and the shift is sort of like the time-space component. And they incorporate the diffeomorphism gauge invariance of GR. Now, in this kinematic phase space, we find the on-shell surface where all of the constraints hold. And from that we can construct the physical phase space by fixing a gauge, for example, or by just taking gauge invariant functions only. Now, what are the constraints in this case? The first set that we have is the primary constraints. So the ones that come from doing the Legendre transform. And these just set the conjugate momenta of the lapse and the shift to 0. What this means is that the lapse and shift are perfectly arbitrary functions, and they don't participate in the dynamics. The secondary part is this constraint here, HA. This is what needs to be, and these secondary constraints need to be conserved in time, need to hold so that the other constraints are conserved in time. And the first of these is the spatial diffeo constraint, which is very, very similar to the Gauss constraint of electromagnetism. So there it was that the electric field is divergence free, but in GR you rather have that the ADM momentum is divergence free. So this is called the spatial diffeo constraint for reasons that will become clear later. And then there's a fourth constraint. So these are three, one for each spatial direction. And there's a fourth constraint called the Hamiltonian constraint, which looks a bit complicated and very, very much not like a Gauss constraint, and which really is the star of the show. This is, at least traditionally speaking, the hard part about GR. This is the difficult constraint. So what we have here instead is more similar to the constraint we had in the relativistic particle, which read this. If you remember, this was the constraint we had to impose so that we have time reparametrization invariance. And in effect, it's just the on-shell condition for the particle. Here, it's kind of similar. You still have something that's quadratic in the momenta, and you have some kind of weird metric which you use to contract them together. And you have something which it's equal to, and which does not depend on the momenta. So this is sort of like, you could maybe think of this as a mass term. And then you could really think of GR as something like a relativistic particle moving in a metric, moving in a space which is equipped with this metric here. But importantly, this depends on the metric itself. So it's not really a mass, and it's really more like a potential. So it would be sort of that we replace p squared minus m squared by something like this. Of course, though, if you happen to be in a subspace of metrics and so forth, where this is where the scalar curvature here is constant, then you can again interpret the constraint as just being something like a mass shell condition. So for certain restricted sectors of GR really behaves like a relativistic particle. That's already the first very interesting insight. Now, what kind of space would this particle be moving in? So, as we remember, the original relativistic particle we had was some kind of curve injected into some space-time. And give me a second. Was ist los? Ich kann nicht, ich bin am Vortragen. Okay. So we had that it's a curve injected into some space-time. And here instead we have that it's a metric which is a curve into a space of metrics on the given spatial slice. So the space-time, in quotation marks, that GR is moving in is the space of metrics on a given spatial slice. So in a sense, you can say GR is a relativistic particle on metric of sigma. That's one way you can interpret the dynamics of GR, at least in a restricted sense. And then you can also say, if this is a potential in which the particle is moving, then it's a potential that lives on the space metric of sigma. What the space actually looks like, particularly with whatever metric you put on it, that's a complicated story. But it's been studied in the 60s, and people really did consider this interpretation very seriously. Now, what is this metric in particular? So what's known is that this here is the metric in which the particle would be moving. There's sort of a very small set of metrics that you can actually use on the space of metrics. It's called a supermetric, and it's known that this has a bunch of symmetries, and it's a very nice system if you exclude certain regions of metrics. Now, that's one way you can interpret it, but I don't want to get further into that. What I instead want to show is, what do these constraints do? So the first thing you can do is ask, okay, the primary constraints here, they don't do much. We already know what they do, and they commute with all of the rest. But we need to know whether the rest of the constraints is first class or second class, because that influences how we're going to quantize this stuff and how we can interpret the gauge transformations that they generate. So if you, for example, take the commutator of two spatial Diffie constraint pieces, what you get is another spatial Diffie constraint. So this is already a closed subset. Second, what happens if you use a time-like diffuse constraint and a space-like one? You get another time-like one. So that's also like almost closed. Now, the last piece is a bit more problematic. It turns out that if you take a time-like diffuse constraint and take the Poisson bracket with another one, you also get one, but it sort of has very non-trivial structure constants. Usually what you would like is that your constraints have a sort of Lie bracket structure where these things here are constants on phase space. And in that case, you could use a lot of machinery that's already very well established. For example, you could use the BRST quantization technique and basically not change anything. But this is not the case here, because in the case that we have in GR, these coefficients depend on the point that you are in phase space. So they depend on the metric and the momenta. And this is what's called structure functions. This is not all bad. It means it's still closed, but closed with the caveat of having structure functions. So the point is, this is still first class. This is still a first class set of constraints, and as we saw last time, first class constraints generate gauge transformations. This Dirac algebra is known from several corners of physics and math, and it's known that at least on some level it should be related to diffuse. But this naive expectation, let's call it, that if you take some vector field xi and split it into a space-like and a time-like part, and then just use it with these constraints to generate something, and that should give you just diffuse acting on whatever function you have, that turns out to be not correct. So if you want it to be strict, it means that the gauge transformations of GR are not diffuse. I will expand upon that a bit later. The first point is that for spatial diffuse, if you act with the gauge transformation on some function of Q, of the metric or of the momenta, then you get the same thing that you would expect. So the spatial diffuse constraint gauge transformations are actually spatial diffuse. But for the Hamiltonian constraint thing, this is not true. At least not obviously so. So what turns out is that, well, say you want to try and see what does this constraint do? What does this generator do? Does it generate time translations? Does it generate time diffuse? And you apply it to some function of the metric. Then what you get is that it generates something which does not look really like a time-like diffuse. It does not really look like a time-like diffuse, but via some very complicated computations, when you impose all of the constraints, then it again works. So on shell, as we say, this does actually generate time translation diffuse. The same thing also applies for the momentum itself, but the expression is, well, it's quite complicated. There are many different pieces in the full expression when you calculate the Poisson bracket, and only when you impose all of the constraints does it give you a time derivative. So only on shell do these constraints generate what we would associate as Diffie gauge transformations. So the true gauge transformations of GR are actually something more like what's called the Bartman-Komar algebra. And this is exactly due to the restriction we made much earlier in the very beginning on having only space-like foliations which are future directed. So because of that, we have the situation that spatial diffeos are perfectly fine, because any spatial diffeo just turns a spatial foliation into another spatial foliation. But time-like diffeos, foliation changing diffeos, so to say, those cannot change the foliation by too much. They can only change it so that the normal vector of each slice is still looking in the time-like direction, and it cannot reverse it. It cannot reverse the time direction, and so forth. So what you end up with is not quite diffuse, but it's sort of a very small subset of diffuse, which if you still impose all of the constraints on the data, does actually give you the same thing. So there's a few different things you can do to understand this. The first is you can go back to the relativistic particle, and you can say, okay, or just the non-relativistic even. You just take the usual non-relativistic particle, and you find that when you take the Poisson bracket, it actually gives you, well, P over M. It doesn't directly give you the time derivative of x. It only gives you that time derivative if you know that this is one of the equations of motion. In the Hamilton formalism, this identification is something that only holds when the equations of motion hold. So in principle, this is the same thing as in the basic Hamilton formalism. You have something which you would call the Hamiltonian, and you apply it to some function that you hope will give you the time derivative. But only when you impose the equations of motion do you actually see it to be the time derivative. Now, the difference in ADM is that you have two different ways of acting on the foliations and on the data. The first is just by brute force acting on the system and changing the foliation, which would be an action of diffuse. On the other hand, you have an action of this Bartman-Komar group just by taking Poisson brackets with the constraints. But on the physical phase space, all of this stuff agrees. So, to summarize this quite technical part, what is important for GR is not diffuse per se, at least if you want to quantize stuff in the usual fashion. The diffeo invariance of GR is quite generic in the sense that there's a million different theories of gravity or of metrics, let's say, which all have diffeo invariance. It's not a hallmark of GR. What is a hallmark of GR is this Bartman-Komar algebra and the specific form of the constraints. So what you will find, for example, if you change from GR to f of r gravity, is that the constraints will take a different form. And this is how you know that you have a different theory of gravity. Now, in principle then, if you want to be straightforward, what you want to quantize is not the Diffie symmetry, but the Sparkman-Kolmar symmetry. And only in some sort of semi-classical sector where the equations of motion, the classical equations of motion hold sort of very, very cleanly, only there do you need Diffie invariance. But importantly, this is only true for ADM. If you do something where you include also more general foliation changes, more general foliations overall, then this will be different. And what's also very important is that if you don't impose the constraints, you don't just have a plain way of having time evolution. You will not just have a way to say, I push my slice up by 10 minutes. And instead, you will have to go on shell first. Now, as a remark for path integral stuff, say you are of the constitution that you don't like canonical stuff. You just want to take metrics. You put the Einstein-Hilbert action there. You just say, I mean, I can just like somehow make sense of this path integral. I just write it down. I take some sort of semi-classical approximation. I only take the saddle points of the path integral, and that should be good enough. Now, the thing you have to keep in mind for that is that in principle, you don't want the measure here to be Diffie invariant. What you want is that the measure of the path integral is invariant under the Sparkman-Kolmar algebra. That's the main thing to keep in mind. And yeah, okay. That's already part 4. Now let's get to something a little bit more enjoyable, which is you've seen the constraints. They look quite ugly, but can we actually solve them? So for the example I gave in the last talk about solving about the relativistic particle, if the measure isn't diff invariant, how is it not inherently problematic? Because, as I said, diff M is not an off-shell symmetry of the canonical formalism. However, if you're... Okay. Babs asks, if the measure isn't diff M invariant, how is that not inherently problematic? I may have been distracted about the necessary difference between diff M and Barkman M. The difference is that if you look at this off-shell phase space, which you would usually quantize, for example, you just put hats on the metric and its momentum, and also on this other stuff here, then you don't have an action of diffuse on this phase space. At least not one that's represented by Poisson brackets. Instead, what you have is that the phase space has certain gauge invariances coming from the constraints here. So you know that whatever h here is and whatever this h here is, they generate gauge transformations. And when you check what these gauge transformations actually do, then you see that it's not diffuse. You see that actually it generates this kind of complicated expression here, or this complicated expression for momenta. So conservatively speaking, the gauge symmetries of GR, at least in this canonical formalism, are not diffeos. It's the spatial diffeos and these slightly weird transformations that represent time-like diffeos. So that's the symmetry that you would have to put into a quantization. That's the stuff you need to gauge fix. But if you, so there's really, so because you don't need the measure to be diff invariant. Yes. So there's basically two ways you could go about it. The first way you could do it is to say, okay, you know that BKM is your off-shell gauge symmetries. So you have two ways of going about with this. The first is you solve all constraints to get some kind of physical I'm already running out of symbols to use. So you say you solve all of the constraints and you end up with just physical degrees of freedom of GR. And then you quantize that. Then the theory is BK M invariant. But because you're on shell, this is diffeos. So that's the first way you can do it. The second thing you can do is you quantize first. Quantize kinematically. So you take Q and P and you just put hats on them. And then impose H A on physical states equals 0. Okay, yeah, before I address the question, I'll finish real quick. So if you do this, then this would be something you do in a path integral. Right? In a path integral, you sum over all configurations. Not just the ones that solve the equations of motion. So in this case, you would have to have the Barkman-Komar algebra here. And then the semi-classical piece of this path integral would be the one of GR, where you have diffeo invariance. But it's more related to the difference between quantizing first and then imposing constraints versus imposing constraints and then quantizing. So those two theories will give you different theories. So those two prescriptions give you different theories, but if you make your path integral have this invariance, then you have a bigger chance of having it agree with the other prescription. Now, I might be far afield, but is there a way I can interpret the diff M versus Barkman-Komar M difference in gauge group as some kind of anomaly? I don't think so. The main point that needs to be stressed is that this comes from restriction of the foliations. If you allowed all diffeos to act on this phase space, then they could also change a space-like foliation into a time-like one or a light-like one. And this is not allowed from the get-go. So the difference between the two is really that Barkman-Komar is the symmetry algebra of metrics evolving in time, such that when you impose all of the constraints, it gives you back the original symmetries. The difference is a gauge fixing in order to prevent mixing time foliations with others. Huh? I guess, sort of. Maybe not fixing, but something of the sort. Maybe something like a gauge separation. Like you separate all possible gauges into like 3 categories or 6 categories or something like that. So like space-like, light-like, time-like, and time-like you divide into future and past-directed, and then you restrict to only the future directed time-like foliations. Yes. It's something maybe more like, I guess the closest thing that comes to mind about this is like the, what's it called? A Gribov sector, I think. Like there's this thing in Yang-Mills theories and general non-abelian gauge theories where you cannot choose a gauge, like a global gauge fixing for all possible field configurations. And in a sense, then you have to separate the the set of configurations into like different zones on which you have separate path integrals. One for each like patch where you can fix a global gauge. Maybe, but I am not sure if those are instanton sectors or something else. But either way, let's go on to the sort of the more enjoyable part, which is, can we actually solve those constraints? So there are 2 ways, as I said, to quantize a system which have these constraints. The first is you understand the physical phase space, the physical degrees of freedom, and quantize only those. The second is to quantize only the kinematic of phase space, so of spatial metrics, conjugate momenta, and so forth, and then impose the constraints on the quantum level. Those 2 are definitely not equivalent in general. There are many examples where this has been shown. It's, for example, known that the second idea, has a few more observables than the first. But it's a subtle issue, and it's only known in relatively simple models. Now, the first of these 2 approaches is called reduced phase space, because we first reduce to the physical degrees of freedom and then we quantize. But for that we need to solve the constraints. And as we saw these before, they look quite complicated, but luckily it is possible to fully solve them. The first is the spatial diffeo constraint, which says that the divergence of the momentum is 0. You can solve this exactly. What you want to do for that is to first split the momentum into a symmetric part which doesn't have a trace, which I call S here, and into a part which is pure trace. So something which is just like a metric times some constant. Now, any trace-free thing is which satisfies this is perfectly fine, and any such T is also fine. Really, any, because because the metric part here is already covariantly constant. So what you have is, for at least for the spatial diffuse constraint, is that this tau here in the split, let's write it as, come on, no. You can write PAB as SAB plus tau QAB, like this. Then there's no restriction on tau, no restriction whatsoever. And there's only a mild restriction on S here. In principle, what you then have is, well, these are free initial data. They can be freely specified. And they amount to a sort of mean curvature of the slice. And the S part, which is in effect identified with the degrees of freedom of gravitons. So if we, for example, take the phase space P, which originally has 6 degrees of freedom, but there are 3 degrees of freedom removed from the constraint. Then there's 2 degrees of freedom in S and 1 degree of freedom in tau. So per point, once you have imposed spatial diffuse invariance, you have 3 degrees of freedom per point. So there needs to be, you need to remove one more in order to arrive at the free data of gravitons. The Hamiltonian constraint is a bit more difficult to solve, but there's a method which was invented in the late 60s by York and some of his students, which is called the conformal method. The idea is that you take the diffuse constraint, the spatial one, and notice that if you take a metric and its conjugate momentum and you rescale them, so you do a Weyl rescaling, you just sort of change all of the lengths without changing the angles, then the spatial diffuse constraint is covariant under that. So solutions are mapped onto solutions. But the Hamiltonian constraint is not invariant. And this allows you to take an initial solution, change it by some Weyl rescaling, and then see it as a differential equation for this rescaling factor. What this means in turn is that h equals 0 determines the scale of the metric Q. So in effect, what you have is that the Hamiltonian constraint selects out of all possible metrics which satisfy spatial diffuse constraint a certain one where the local sense of volume is given by some algebraic equation. So or some differential equation actually. What does this look like? So if you, for example, take some reference metric Q bar and just write a general metric with this prefactor here, and you split in a similar way the momentum into this S part from before, this tau part from before, and some extra vector field piece, which is additional gauge. Then you can insert this into the Hamiltonian constraint equation, and you find two equations. You find, first of all, that in order to solve the spatial diffuse constraint, you have to solve for a certain vector field, so you don't have to put any restrictions on S. The second piece is that you can solve for this scale factor of the metric through a kind of differential equation which looks a bit like a Poisson equation. And for example, if we look at metrics which are which have constant curvature on a slice, then this is like a Helmholtz equation. In principle, what this means is the Hamiltonian constraint can be solved if you first start from some initial data given by these objects here. So you give me a metric, you give me an S and a T here, and then you solve first for this one vector field psi here, and then you also get a differential equation for phi. And as is typical for Poisson-like equations, if you provide some boundary values to it, then there's a unique solution. So it's known that if you give some free initial data in this form, then the constraints can be basically always solved. And for certain classes, this is already very well studied. The case that is most well studied is the so-called CMC, or constant mean curvature class of solutions. So in principle, we know how to solve the constraints of GR and arrive at the physical degrees of freedom that evolve in time. Let's do some counting to see how many there are. First of all, we have in S, because it's trace free, we have 5 degrees of freedom. It's a 3 by 3 matrix. It's symmetric, so it has 6, but minus trace gives us just 5. In that case, we have, say for the constant mean curvature case, we have one equation. Wait, it's symmetric, so this is actually three equations. Yes, there are 3 equations, which leaves S with 2 degrees of freedom. Tau, on the other hand, also has 0 local degrees of freedom, if you choose this particular thing. And you can also see it as a gauge fixing for the Hamiltonian constraint. Next, for the metric itself, this has 5 components, again because it's symmetric 3 by 3, but also because in order to set it apart from the scale factor, we have just fixed its determinant to 1. This thing, because you have spatial diffeon invariance, you can gauge fix 3 components, which means you are left with 2 degrees of freedom. And similarly, as for tau, by using the Hamiltonian constraint equation, you arrive at a unique solution. So there are 0 degrees of freedom from it left. So in total, we have that when we impose all the constraints, we have 2 plus 2 degrees of freedom on the phase space. And if you know if you've heard about gravitons, those are m equals 0, spin 2 particles, and those have 2 polarizations. So what you get in this completely non-perturbative picture is that when you impose all of the constraints, then at the end you are left with still just 2 polarizations of gravitons as local degrees of freedom. So it's sort of true that gravitons are a feature of perturbative GR, but at the same time, you can find those degrees of freedom also in non-perturbative GR. In total, what you have is that there's 6 plus 6 coordinates. So the phase space is the kinematical phase space has 12 degrees of freedom at each point. But by 4 constraints and 4 gauge fixings, you remove 8 of those and are left with the 4 that we saw above. In principle then, if you gauge fix all of the data, so you gauge fix some part of the metric, and you leave the degrees of free, and you require that S here is divergence free, then this is the data of gravitons. In principle then, if you prescribe such stuff, then you can always time evolve it and get something that, well, looks like gravitational radiation moving about. Of course, it depends on what initial data you choose, but then you can get many different resulting spacetimes. So in conclusion, we have that initial data is of GR is given by a conformal class of metrics. What does this mean? This means any metric which is related to another metric by some positive rescaling is regarded as equivalent. In particular, what this means geometrically is that the lengths are not part of the initial data of GR. What is actually part of the initial data is relative lengths. So if I give you 2 curves, or rather let's have them start and end at the same point, just for simplicity, so you can compare stuff. Then the initial data of GR does not care what the total length of either of these curves is. So L1 and L2. But what is initial data is L1 by L2, because that's invariant under changing the total scale of the metric. In particular, what's also invariant and part of the initial data is the angles. So angles are part of the initial data of the geometry of GR, and relative lengths are part of the initial data. So this is stuff that you can freely specify. This is the stuff that the dynamics of GR is really about. Similarly, you can also specify this transverse traceless S here and the mean curvature. All of these things are sort of things that you would find in the quantum state. In particular, and this is very important, the actual total length scale is fixed by the dynamics of GR. So if I provide you now some quantum state, then it will be labeled by such a class of geometries. It will be labeled by such an S, and it will be labeled by such a tau. And then if you want to have an observable for L1, L2, so a relative length, then this is well defined. This makes sense. But if you want to have the actual full total length of a curve, then you need phi first. And phi is given as the solution, as some sort of complicated operator that depends on the other data that the state has. So in some quantization of gravity, the states will be labeled by this data, and there will be some operator which tells you some operator which is a function of the other data, which allows you to compute total lengths. Mind you, this is for spatial lengths and so forth, so no space-time stuff. Of course, anything that applies to lengths also applies to areas and volume and so forth. Now, there's a second approach for solving the constraints and quantizing stuff, which I said I will skip due to time constraints. Right now, it seems like maybe I can do a little bit of that. But first, I will just give the naive picture of it. I think most of this will just stay the naive picture. The naive picture is that, okay, we just sort of take Q and P, QAB, PAB, and we turn them into operators. And then, okay, we have states which are labeled by a given metric, by a three-dimensional geometry. And then we can take some generic state in the system, take the inner product with such a sort of position eigenstate, and that will give us a wave function. But in this case, the input to the wave function will be not just something at a single point, but just a whole configuration of the metric all over space. And this is what's called a wave functional. And these wave functionals, again, need to satisfy the constraints that we noticed before. And so the hope is that we can write down these constraints in terms of just operators acting directly on the Hilbert space. In this approach, we would say, okay, the ADM momentum should have canonical commutation relations with the position, which is the metric. And so we write it as a derivative of the wave function by the metric. That's all fine and good, at least if you write it down formally like this. And then the spatial diffeo constraint sort of tells you, okay, you take the derivative of the wave function with respect to this one metric coordinate, and then you also have some sort of covariant derivative that acts on this, and this needs to be 0. That's maybe difficult to implement, but it's not impossible. I think I can actually show you a way later on. So what this implies, on the other hand, if you turn this around a little bit, this translates into a statement of gauge invariance for the wave functions of GR. So in principle, all that really requires is that the wave functions of GR, so wave functions of the metric, need to be invariant under this under spatial diffeos. So they need to be gauge invariant. There are some subtleties here which come from anomalies of implementing this gauge invariance condition. But for the naive picture, it's well enough to just imagine, okay, fine, we have this we have wave functions, we require them to be gauge invariant. Makes sense. Now for the Hamiltonian constraint, you have what's called the Wheeler-deWitt equation. This really is just, you take the Hamiltonian constraint, you turn it into an operator, you act with it on a wave function, you require that to be 0. Ideally, that works. So what would that look like? You sort of take the wave function, you act on it with some momentum operators. You have this metric here, which depends also on position, but because we're working in the position representation of wave functions, this will just be some diagonal, so it will just be some function of Q. So, I mean, this looks complicated, but it seems doable, right? So it would be similar to if we took in the relativistic particle case, if we took states labeled by positions of the relativistic particle, and then we took wave functionals of the position, the fourth position, and then required the constraints p squared minus m squared psi is 0, which would translate into sort of minus del by del x mu, del by del x mu plus m squared psi of x is 0. And well, if you rewrite this in a little more suggestive fashion, then what this is minus box plus m squared psi of x is 0. And would you look at that? That looks like a Klein-Gordon equation. So in the relativistic particle scenario, which again is very similar to GR, what imposing this Wheeler-DeWitt equation amounts to is you take wave functions which satisfy a sort of gravitational analog of the Klein-Gordon equation. But again, it's wave functions, and it's known from QFT stuff that wave functions satisfying these wave equations are sort of not really the full picture, and you should be careful in interpreting what any of this means. You should certainly not interpret these as equations of motion of some field. Now, actually working with this sort of quantization is very difficult for a number of reasons. Many of them are very technical. But DeWitt's papers, which basically are all called quantization of gravity, all show you can do a lot more stuff than you immediately think. The main point, if I remember right, and now we're getting into like semi rambling territory, is that you can take the full space of metrics and you put this Wheeler-DeWitt supermetric on it. Well, it's a metric, so there's a certain notion of lengths on it. And in principle, what you would like to do in this approach is to see the motion of GR as having some sort of geodesics on met m, or met sigma, right? Sigma. What do these geodesics look like? It seems that the geodesics have a sort of strange shape, in that there's a sort of, that the metric has a horizon. A horizon in the same sense of GR, so that geodesics all sort of end there very abruptly, similar to what a real singularity does. So what seems to happen is that most of the trajectories of such geodesics actually start on the horizon and end on the horizon. But if you want to see that as time evolution, that is a bit strange. It's a bit strange in that you start from something where this frontier here which corresponds of metrics where the determinant vanishes, it sort of tells you that you sort of start from a metric which is degenerate, then you evolve into a normal regular metric. You kind of follow it along the evolution. This is the real time evolution of GR. And then eventually your metric just kind of collapses back in on itself. That sounds a bit weird, because you would like your metric to stay regular at all times. That's sort of like a starting assumption. But there's actually a way in which this makes total sense. So if you take, for example, some slice, and you say this is my spatial slice at time t naught, and then you just follow it time evolving, then you end up with a different metric. So this is q at t naught, and this is q at t1, and so forth. Now what this evolution tells us is that at some point at possibly finite initial time, or maybe infinite initial time in the past, the metric degenerates. So q of, let's say, t minus, this has determinant 0. This is a spatial metric which has determinant 0. That sounds a bit weird. And further, if you follow into the very future, you have the same thing there. So you have that determinant of q at t plus is also 0. Now, this is interesting because this is precisely what you would have in a Big Bang and a final Big Crunch. If you know a bit of cosmology, you know that the scale factor is sort of the stand-in for the determinant of the spatial metric. So if the determinant of the metric becomes 0, it means the scale factor becomes 0. And that's precisely what happens at the Big Bang singularity. Similarly, a Big Crunch singularity also has that a of t equals 0. And if you take this sort of picture here, this sort of space-time, and you think, okay, I'm gonna take this as my time evolution, and I'm going to like deform it a little bit to see what it looks like to see what it actually represents as a geometric object, as a 4-dimensional manifold. Then you can deform it and sort of see that what it actually corresponds to is a sphere. So it's a sphere in that if you take a slice here, then it corresponds to some slice here. All of the slices look the same, apart from the points at the very end. So the points here at the very end, those will, of course, if you just slice them vertically, they will have 0 volume. They will have 0 area. And that's perfectly fine, because they're just the endpoints of your sphere. And you've sliced it in a certain way. So what this tells you is, generically, Generically, the full space-time evolution is more like a sphere. So for example, when your sigma, your spatial slice, was actually a 3-sphere, then the time evolution will be diffeomorphic to a 4-sphere. You can also do this differently. You can do this with a 3-dimensional torus and other stuff, but the picture basically stays the same. So you can make a few interesting remarks about the full behavior of GR under time evolution when you do it in this particle on the space of metrics picture. And given that this is really one way to interpret the dynamics of GR, we know that under certain very simple circumstances, like in cosmology, that really GR will behave a bit like this. Now, I have a bit more time and I don't want to overextend, but I want to give you a bit of a cool example on solving the constraints symbolically. The idea is that you have some sort of wave functional. And what you would like to do is you want to write it not as well as some explicit function, but you use a trick. You rewrite it as, well, I need a letter, sigma. Yeah, sigma is good. You introduce a path integral which depends on sigma and which has Q as a source. So in particular, because it's the 3 metric, we will say that there's some kind of energy momentum tensor that the metric couples to. And if you write a state in sort of a path integral form like this, then you can, for example, take the spatial diffeo constraint. So you use this as an ansatz. You first take the derivative with respect to the metric. So ij at point x. Now, what does this look like? Well, you rewrite again. There's this path integral. And well, let's put a minus I here so that we have the full momentum operator. You have this exponential. And by deriving with respect to q, we get from this exponential an insertion of the energy momentum tensor. And what does this look like? Well, if we forget about normalization a bit, then it means you can take the action of the momentum operator to just be the same as the action as taking an expectation value of the energy momentum tensor of this sort of auxiliary field theory here. So the point is that, in a sense, if you write your states as path integrals, mind you, path integrals on the spatial slice, so Euclidean path integrals, then, so psi prepared via Euclidean path integral on sigma, then the operators pi ij are equivalent to the operators tij. So any operator that acts on the space on the Hilbert space of general relativity will be something that you can convert into an operator of such an auxiliary path integral. And then if you do that, what does that imply for the constraints? Well, as we said, it needs to be that the divergence is 0. What does this mean? This is equivalent to requiring that if you take in this auxiliary field theory, which defines a state, that the auxiliary field theory has a conserved energy momentum tensor. Give me a sec. Hi. Danke dir. So, in principle, what this means is any field theory on sigma with conserved Tij defines a state of GR on sigma, well, up to the Hamiltonian constraint. And in principle, you can find many, infinitely many different field theories which all have a conserved energy momentum tensor. For example, any translation invariant, if the slice is sigma, is R3, any translation invariant theory will do. So this should tell you that there are lots and lots of solutions to these constraints, and you can interpret them in terms of path integrals, for example. This is something that is done in other contexts, for example, when people study other theories that also have Diffie-Hellman invariants. topological field theories. Such as Chern-Simons theory. What does the Hamilton... So to cap this off, and then I think we can stop for today. What does the Hamiltonian constraint do in this picture? Well, in this picture, it would amount to G times P is given by R of Q. Chern-Simons isn't topological because of the framing anomaly. It's yeah, sure. In this corner of physics, we work with trivial bundles. So here, the equivalent statement would be that we take this auxiliary field theory and we take a combination of the energy momentum tensors. So overall, what this says is you can find many different solutions to the equations of to the constraint equations. Also, in this sort of quantize first, impose constraint second approach, just by taking just by first quantizing and then writing your states in this sort of intuitively a bit strange path integral form. And then in this path integral form, it just requires a few constraints on the field theory. In particular, it requires that it has conserved energy momentum, and it requires that there's a certain identity of the correlator of the energy momentum with itself. So I think this should be enough for today. What I wanted to demonstrate with all of this is two things. The first is the subtleties of the constraints of GR. So in particular, what the gauge transformations of GR are, if you really pay attention to the details of it. And second, that the constraints, no matter how complicated they are, definitely are something you can work with, and that solutions are under control. Of course, in principle, you would need to solve this complicated differential equation exactly in order to have all of the constraints completely solved, which in practice is not possible. But in certain situations, it is very well understood what the solutions look like, and you can do lots of analysis even then. And even if you don't want to solve the constraints on that level, if you say, I don't care, I just want quantum gravity, I want to start right away, I want metric operators, I want to do complicated operator stuff, then even then you have some idea of what happens. You have this idea that that for certain subsectors the evolution of GR is like geodesics on the space of metrics, and you can get some ideas about cosmology from that, which however you can also get from classical GR. And it's also possible to find quantum wave functions of the metric if you just insert the right kind of field theory as an ansatz for writing the states as path integrals. Overall, this should give you the picture that we have a very concrete understanding of what the degrees of freedom of GR are. In particular, that gravitons are something you can sort of see also in this non-perturbative formulation. But writing them out explicitly is something that is probably beyond anyone's individual capabilities. But even still, all of this is very much sort of like under control. If you really want to get into the nitty-gritty details, it's of course very complicated, but it's something you can in principle work with. And so that should raise the question, what really is the problem of quantum gravity? And that's something that I hope to get into in the next sessions, where we will talk about observables, so sort of what you can actually compute, and also what kind of problems you have overall in formulating questions in this sort of theory. And then I hope in the fourth and last session we will get some overview of like modern approaches to QG. And if you stay around for that stuff, then I think you will appreciate having seen all of this technical stuff before, because that will be a lot of relevant context to see why people try out different stuff. And also that even in a very mundane way, you can proceed quite far. And you don't necessarily need to like go all the way to stuff like emergent space-time and all that jazz, if you really don't want that. I also hope that in the last session we can do some pheno stuff. I hope to get a bit of quantum cosmology in there. Perhaps some other stuff as well. I'm not quite sure. There's some interesting papers about proper quantum effects of gravitational fields, which however are non-relativistic stuff. But it would still be interesting to talk about potential ways to actually verify and make experiments with this stuff. So I hope I can get to that near the end, and maybe then it will not be as dry as it was today. So thank you all for listening in, and I hope you stick around for the next sessions. Next week, same time, probably.